Hello guys, it's Tony here, and today we'll be doing a few IB problems. So, why don't we get started with number 4. So here, oh shoot, am I in the... Yeah, let's switch over to the questions tab. So number 4 here, we basically have to solve a differential equation, and we are given dy over dx equals to x plus y. And so when I see this problem, you would immediately jump to thinking, oh hey, we have a dy dx on the left here, right? How can I manipulate this so that it can be reduced down to a function? So when I see this, I would think about moving the y to the left side. So we would get dy over dx minus y equals to x. All right. So let's jump back right into the whiteboard and let's write this down. So how I would do this is I would take the dy dx minus y equals to x, so that we can put this entire differential equation in the form dy dx plus p of x over times y equals to q of x. And since q of x doesn't really matter what it is right now, we can have x be the q of x in this case. So at this point, we know we gotta use integrating factor to solve this problem. So let's get that started. So I of x equals to e integral of p of x. And since there's only a negative, we can just say that's a -1. So this will be e integral -1 dx. So we can do e negative x, as that is the integral of this. Alright, so now we got our integrating factor. We can multiply that with pretty much everything here in the differential equation. So we would get this minus e negative x y equals to e negative x x. Alright, so now we would be getting the the derivative version of this left side. So we will have d dx e negative x times y. And then on the right hand side, we would be getting the integral of this entire thing. And the reason for this is that we'll be actually taking the integral of both sides so that we can get rid of this derivative here on the left. So on the left side, we'll be getting e negative x times y equals to this integral. So yeah, let's see if we can solve this integral on the right. How we're gonna be approaching this one is with a integration by parts. So let's actually clear the canvas here so we get more room to work with. So e negative x times x, integral of that. I'll be following the Liet rule, so the algebraic will go first. So we're gonna have the x as the derivative, and the e negative x, because it's a exponential, it will be the integral. Alright, so let's get this set up. So we have derivative of x is 1, and derivative of 1 is 0. And here it just repeats with a negative. And so there we go. We can take these two values, so it will be negative e negative x times x minus e negative x. That will be the integral of this. Perfect. So now let's go back to our equation. We have e negative x times y equals to negative e negative x minus e negative x. And of course, we can't forget the plus c. We should write it here as well. Okay, so now we can divide this e negative x across the whole thing, which will leave us with negative x. Where's my x? Oh my gosh, I'm forgetting everything today. Okay, and we get c divided by e negative x. Since this is in the denominator and there's a negative, this goes out. Alright, so now we can try to find the c. It is given that y equals to 2 and x equals to 0. So that is perfect because we can plug this right in. So 2 equals to 0 because it's x minus 1 plus c times e to the power of 0. So this will be 1. We cancel that out. And now we're left with c equals to 3. And I think we have it. Y equals to negative x minus 1 plus 3e negative x. And that is our answer. Alright. Question part A asks us to use Euler method to find this equation when x equals to 5 pi over 12. And we do have all the information. We have the initial values for x and y, we have the step, as well as we have the differential equation itself. So let's jump over to the whiteboard. So I have pretty much written this out already. This is for the TIA 84, I believe. And you pretty much will be able to just plug this in on the top. And for those of you who are experiencing errors, I actually plugged an absolute value here. How you do this is you go to you go to math, you go to the second one called num, and then there should be the first option called ABS. You click on that, you put your tangents inside, and then that should fix that problem. So yeah, if you're having trouble, you can plug this into your calculator. So what we're gonna do next, after you plug this in your calculator, is go to second graph. There should be a blue text with the saying label on, with a saying of table on it, and then we can go to u equals to 5 pi over 12, which is the x in this case, and it should be somewhere around 1.309, and that should be second step. Hence, we are able to get the y, which is 1.98. 1.98. Alright, let's take a look at the second part B. If you need to pause the video, please do. Alright, cool. So for part B, we're supposed to show the derivative of 1/2 ln cot x equals to negative cosecant of 2x. Alright, so this is a show that question, so we gotta be converting the left side to the right side. Alright, so let's jump back to the whiteboard. Oh, I'm actually on the whiteboard here. Okay, so we have derivative of what was it? 1/2 ln, I think it was cotangent of x, and we're trying to make this negative cosecant 2x. Alright, so what we're gonna be using here is we're gonna be using chain rule. So what we're gonna be doing is we're gonna make 1/2. That's the 1/2 in front. I don't know why I made that so big, but since this is ln, we take a derivative. This will be cotangent of x. And using chain rule, because the derivative of cotangent of x, I think is negative cosecant squared of x. Yeah, so what we can do now is we can simplify this to 1 over 2 cotangent of x, and the 1 can be multiplied with the -1 and the cosecant squared of x. Now, since cosecant squared of x is 1 over sine x squared, and cotangent x is cosine x sine x, they actually can cancel out to each other. So what we're going to be left here with is, let's see, negative 1/2 times, so we have 1 over sine x. Let's work this out. So we have 1 over sine x squared. We have 2 times cosine x over sine x. Let's distribute these accordingly. We would have, wouldn't we cancel this out? Alright, it's 1/2 times this. So this 2 doesn't exist, it's just this times this. So yeah, okay, this will actually work. I was waiting for a second. So this will be sine x, and these two sine x's cancel out. Not cancel out, but there will be one sine at the bottom. So this will leave us with 1 over 2 cosine x sine x. And through the Pythagorean identity, I believe, we are able to simplify this. Identity, right? Let me double check this identity. Yeah, it's actually double angle identities. Okay, so this will be sine 2x equals to 1 over sine 2x. So with 1 over sine 2x, I know you guys can't see that, but that would give us cosecant 2x. I think we forgot the negative. Yeah, it's supposed to be a negative all the way. We gotta bring that over, and boom, we have the answer to right. Alright, cool. Let's move on to number C. Alrighty, let's take a look at number C. So we're gonna show that square root cotangent x is the integrating factor for this differential equation. Alright, so I feel like there's a very interesting trend with IBQ questions because it kind of uses what it already gave you in front, right? So we can pretty much, because since this is dy over dx plus p of x y equals to q of x form already, and we can see the negative cosecant of 2x here, we can pretty much already just replace that with this. So how is that going to look? Let's switch back to the whiteboard. So we're trying to prove that square root of cotangent x is integrating factor. Alright, so yeah, we can pretty much essentially just replace negative cosecant of 2x with this, yeah, ln, 1/2 ln of, I think it was cotangent x. Alright, there we go. So let's go back to the formula for the integrating factor. We have e to the integral of p of x, since this is supposed to be p of x, but instead we replace it with this, we will have d dx. Let's just draw an arrow. I don't want to rewrite this again, that will take a while. So yeah, what this will happen is the integral and derivative will cancel out each other, so that would leave us with I x equals to e to, I think, the 1/2 ln of cotangent x, and since this is ln, we can use the property logs to make this the exponent of cotangent x, and since the e and ln, well, they cancel out, so that will leave us with the integrating factor being cotangent of x to the power of 1/2, which equals to square root of cotangent x, and hence shown. Alrighty, so now let's hop back to the questions and let's actually solve this differential equation. So pretty much we're trying to show that it is x square root of tan x, so they already gave us the answer. So now we just have to show how we get that. So let's jump back to Microsoft Whiteboard and let's get started. So we already know that the integration factor is the square root of cotangent x. So now we can just multiply it to everything. So we have cotangent x dy dx minus square root of cotangent x. We have the other one cosecant 2x, I believe, and times y equals to, what is this last one? Let me double check. Alright, square root of tan x, right? Tan x. And this one is cotangent x. And straight out of the bat, when I see tan x and cotangent x, when they're multiplied to each other, we know there's 1 because tan x is sine over cosine, while cotangent is cosine over sine. So these two just becomes 1. So essentially what we have here is we have the derivative, so we have the integrating factor, that's obviously one of the terms multiplying here, and we also have y. So that's the left side, and the right side is just 1. So when we take the integral of this, we get a very interesting function. We have cotangent of x times y equals to x. So when I first saw this, I actually overthought and I made this more complex than these two. But in reality, this is all there is to it. So, and then we can just like divide the cotangent x over here, and then we get y equals to x divided by the square root of cosine x, and then sine x, and you can just flip that, and you will get y equals to x times square root of tan x, and hence we have proved it. Right. Let's move on to the next one. Okay, so the next one involves considering the Euler's approximation method. Okay, so we did that earlier, and that isn't actually a question. Let's take a look at E1. So we can just plug that into this function. Let me do that real quick. So what is that? 5 pi over 12 multiplied by square root tangent. I do the same thing, 5 pi over 12. And then, oh, I'm in degrees. Yeah, make sure you guys switch to radians, by the way. You don't want to stay in degrees. I got 2.53. So let's clear this. Our answer is 2.53. Okay, and let's see what we have here. Considering the gradient of the curve suggests a reason why Wood's method does not give good approximation method. Okay, so this is actually very interesting. For me personally, the way I understood this is actually through a graph, right? So I actually here graphed x square root tan x, and we can see the gradient increasing as the x increases as well. So pretty much what happened is Euler's approximation method with the steps is linear, right? Whereas this is I think it's exponential, so it will be very inaccurate, and hence why at x equals to 5 pi over 12, the less coordinate will be less compared to what it actually is if we use the Euler approximation method. I hope that makes sense. And then for the last one here, it's a deduction question. Pretty much what you have to think of is the change, so dy over dx, right? And how the gradient is pretty much the derivative. So when we think it that way, and we can pretty much look at its function. So we have dy dx equals to y cosecant 2x. I think it's plus square root tangent x, right? And when we take a look at all of these curves, let me actually shift over to Desmos to make it more visual. So we see the red one is the curve itself. You see all the y values are positive, and we see cosecant 2x is also positive, and I'm going to graph tan x as well, and we see at least for 0 to 2 pi, it is also positive. So what this means is that they will have a positive gradient for the entire thing because there's no negative numbers involved in this function, if that makes sense. So yeah, that's how we can deduce it will be positive. Alrighty, so let's take a look at number 6 here. And for this one, we're going to be using Euler's method again. So let's get onto the calculators. Okay, let me actually switch back to the whiteboard. Alright, let me clear this. Alright, so for this one, we are going to be having a step size of 0.1. Step of 0.1, we are going to have the x and y values of x of 0, y of 2, and let's see, we're trying to find when x equals to 0.5. Okay, and we have the dy dx, let me see, I remember it's 4 minus 1 over 10. Let me double check that. 4 minus 1 over 10. Yep, that is right. Okay, so perfect. Now we got everything we need for the calculator section. So for the, once again, do the same thing you did for the Euler method in previous ones. I'm not going to go over that. So let's go over what we need to plug in for the harder ones. So un plus 1, we are going to have u. And, oh, by the way, this is what TI-84 only. If you're a TI Inspire, go look at Cruz's video. She has some stuff for you, but this is what TI-84 is. This is what you need to plug in. So we have the UN and we have the step for the second part, and that's all you need to do. And then for U0, you need to plug in the x value here, so that will be 0. And then for V's, we gotta start with Vm plus 1. This is probably the hardest part, so we want to be really, really careful with this. So obviously, you gotta start with the Vn first, and then we do the step multiplied by this function, right? Well, after to the right side of the dy dx. So let's do a big parentheses of this, and we can just do 4 minus, let's do 2. 4 minus, what is y? Yeah, Vn. My brain's not working. Should be Vn, the parentheses. can divide this entire thing by 10. And 1, 2, 2, 3. Yeah. Okay. So now we have everything covered. And now we just have to plug in v0 equals to 2 from here. And yeah, now we can find the answers. 1 second, I may do this myself as well. Have not done this yet. 0.1, so I'm doing this live with you guys. Alrighty, so we'll find x equals 0.5. The answer I got was step 5, which for y is equals to 2.098. 0.098. Let me double check with the mark scheme real quick to see if this is correct or not. 2.098. Yep, got it. Alrighty. Right, now we solve this differential equation to show that y equals to 4 minus 2e to the power of negative x over 10. And we started with this equation once again. So let's get started. Let me switch. Oh, actually, I am already on the whiteboard. Let's see. Yeah. So here's the question we have, and we're pretty much trying to prove this in the whiteboard. Let's do this. Okay. Let me get this up and working. All right. dy over dx equals to 4 minus y over 10. That is our equation. So how I like to do this is I like to go from the easiest method to the harder methods, like a chronological order, right? So easy method is obviously variable separable, and since we have only one variable here, we can definitely do that. So how I'm gonna do this is I'm gonna set 1 divided by 4 minus y dy here on the left, and I'm gonna set 1 over 10 dx here on the right. So now we can take the integral of this. This will actually be a u sub, so this would be negative ln of 4 minus y. That does not look like a y. Hold on. There we go. That's a better y. And this other side would be x power 10. So one way we can make this a e thing. So e to the power of negative x power 10 equals to 4 minus y. There we go. Now we have a much simpler form, right? And oh wait, I forgot the c. Oh shoot. So we can rewrite a c here. Yeah, because the top part it should be times c, and that can be written down there. Right. Cool. So now we gotta solve for the c. So the very top of the question, it gave us this. It told us where y equals to 2 when x equals 0, right? That is important because we can still apply that here when we solve for the equation. So let me simplify the equation one more step. Actually, that might be easier for us to visualize it then. Because 4 minus ce minus x over 10. Yeah, there we go. And now let's solve for the c. Actually, where did I get negative from? Hold on. Might have made a computational mistake here and there. So we have 2 equals to 4 minus ce, and since this is 0, this becomes 1, so that gets cancelled out. So 2 equals to 4 minus c, negative 2 equals negative c, c equals to 2, and hence we get our equation 4 minus 2e negative x over 10. Beautiful. Alrighty. Cool. So I think we have answered that question, which is good. Now let's see about the next question. So the absolute error in the approximation from part A. So we just solved our equation, and for part A we did x equals 0.5. So let me quickly plug that into my calculator for the, now we have the actual formula. So 4 minus 2 e to the power of negative, I think 0.5. That was the x we did. And 10. Okay, let's jump back here to the whiteboard. For the new one, for the accurate one, I got 2.09. And what was the old one we had? For that one, we did 2.098. So 2.098. Wow, we can go a few more decimals. Okay, so here we have actually 2.09754. All right, so we gotta take the absolute value of this. So what that leaves us with is 4.5. How many? Wait, let's check the sig fig. Okay, it said doesn't say, so I'm gonna go assume with 3 times 10 to the power of -4. That is the absolute value of the error we made in part A. Alright, I hope you guys enjoyed this video and found it helpful. I know I have been studying a lot, but hope you guys liked it, and see you next time. Peace.